math group. We are going to extend the work that we looked at with the little toys that we're making a sequence. We had a rock, an oar, a door, a shovel, and a parrot. I just have the words today. I don't have the actual toys. But what we were doing is we were making a repeated pattern in a long sequence, and we were wondering about what would the 434th entry of that sequence be. And then we could go even bigger, the 1,105,721st entry. So what I've done here is I've just kind of set things up. The rock was the first entry, the oar was the second, the door was the third, and so forth. And once we get to the parrot and finish that off, then we start again. So the rock would also be in the 6th position, an oar would be in the 7th, the door would be in the 8th, and then we keep wrapping around like this. So some things to notice here, in this right-hand column where the parrot is labeled, we have the entries that are 5, 10, 15, and you can kind of get the pattern there, 20, 25, 30, 35, 40. All of the parrots are going to be in the places that are multiples of 5 because there are 5 things in a set and the parrots end the set. So all of the multiples of 5, the perfect multiples of 5, will be parrots. And if we can find an entry in our sequence close to 434 that is a multiple of 5, then we could build up to this 434th entry. So you might notice that multiples of 5 end in either 5 or 0. So 434, the multiple of 5 that is closest to it but less than it would be 430. So the 430th entry would have to be a parrot, and then we'd wrap around. 431 would be a rock, 432 would be an oar, 433 would be a door, and 434 would be a shovel. So the 434th entry should be a shovel, according to this. You might have also noticed that in the shovel column, the units digits are alternating. They will be 4, 9, 4, 9, 4, 9. And so if you have a units digit of 4, you're going to end up in the shovel column for that. That works this time because we have 5 items in our set. It doesn't work all the time, so I want to make sure that you have a strategy that will always work. What will always work is knowing how many items are in a set, knowing those multiples, and then maybe building up to what we need. Another thing we could have done here is do a division. We're taking out complete sets in multiples of 5. So if we do 434 and divide by 5, I'm doing kind of the old school division here. And if you haven't seen this before, you could go look up how to do this. 5 goes into not 4, but 43, 8 times. 8 times 5 is 40, and then we subtract. Bring down the 3 and the 4. 5 goes into 34 6 times. 5 times 6 is 30. And we have a remainder of 4. So you may have seen an answer written something like this: 86 complete sets with 4 extra items on the end. That would mean if we were to draw out the entire table of these, we would have 86 complete rows, and then we would need 4 extra items. That's these 431, 432, 433, 434 is our 4th extra item. That's how we would have found that. Similarly, we could take 1,105,721 and divide it by 5. Same divisor because it's the same sequence repeating over and over again, and see what our remainder would be. We could also notice that 1,105,721 is very, very close to, let me put some more dot dots in here, extending my table, because nobody wants to write all of these out. This is very, very close to 1,105,720, which would be a perfect multiple of 5. And then to get to 1,105,721, we would just have to come over one more entry. So that means that that entry would have to be the rock. So we would have answers at this point for the 434th entry and the 1,105,721st entry. And we have a couple different ways of getting there. We could do long division with remainders. We could do multiples that are close to the entry that we want and then build up or down if we overshoot. We also could have done division on the calculator with this. So maybe we take this one. Let's do 1,105,721 and divide by 5 for the 5 items in the set. And I actually haven't done this, so I'm going to grab a calculator and do that division real quick. 1,105,721 divided by 5. My calculator says 221,144 complete sets, 0.2 and 2/10. And that doesn't seem like it's very helpful because it's not in remainder format. We need to get it in that remainder format. So what we could do is we could take just that 0.2, and remember that if we read it in perfect English, this would be 2/10. And if we reduce that to lowest terms, we would get 1/5. 5 is the number of entries in a complete set, and we need 1, the first one of them. So 221,144 complete sets and one more item out of 5, which would have put us in the column with the rock, just like we thought it would be. So there is kind of a calculator way we can get there as well. We'll have a different style of problem when we do the exponent version of this. And remember that if the number of items in a set changes, that will change our look of our table, and it will also change our divisor. But the process will stay the same.